Mr. Stelios Rozakis, uh, who is the head of the Bioeconomy and Biosystems Economics Lab in the Technical University of Crete in Greece. His teaching and research interests hands-on decision-making, multi-criteria analysis, and mathematical programming applied to agriculture, energy, and the bioeconomy. Mr. Rozakis, the screen is yours. If you can hear us, we can.
Okay. Thank you. Thank you very much. I will upload immediately my presentation.
Perfect. We can see your desktop, and this is, yes.
Now, can you see my?
Yes, perfect.
Okay, can I start?
Whenever you're ready, yes.
Okay, hello to everybody. I will present somehow different work, but it is related to what is presented before, in the sense that we, with my team, have developed models to relate bioenergy to the production phase. So independently of the technological progress, we should never forget that bioenergy has to find input either in the form of residues, waste, or dedicated crops. So in this work, we combine everything using an economic methodology and supported by software that I will talk. This is why in the title of the presentation we mentioned GAMS. GAMS is a frame, a software tool that we use for this purpose. In the case study I'm presenting here has to do with biogas in Poland. So investigated bioeconomy development through economics lenses, the case of agricultural biogas industry in Lubelski area in Poland. And this is the team. This work was developed during my stay in the Institute of Soil and Plant Cultivation in Puławy in Poland, in the Department of Bioeconomy and Systems Analysis. So the background, biogas is a main, let's say, vector of bioenergy development. However, countries are unevenly developed, even if there is a lot of potential. For instance, in the countries of Central and Eastern Europe, some of them are quite advanced. For instance, Germany has a very proactive policy for biogas development. Poland, that has more or less the same potential, is far behind. Well, the situation is a little bit improved the last couple of years, but still there is a huge gap. In Germany, we have about 7 or maybe more plants producing biogas, whereas in Poland is in the order of 100 or 150 or something like this. The critical issue is the competition between bioenergy and other agri-food supply chains. And then we consider the environmental impacts. We aim to develop a tool that was the purpose of the work, to comprehensively investigate the consequences of biogas policies in Poland and assess the most efficient incentive system for biogas production in Poland. So to promote the bioenergy chain that has to do with biogas. and the instrument is modeling dedicated energy crops in complementary to residues. So we developed a supply side agricultural sector model and then combined with the demand side biogas industry. Here is the partial equilibrium modeling framework. So we have the agricultural model that provides, generates supply of feedstock for biogas plants. This depends on the price of energy crops. Then we take into account the technology and transportation. We built the so-called industry model. So the industrial model generates the demand in the region of study for feedstock from the biogas plant side. So the supply and demand are matched, and then the market is clearing, giving prices and quantities. So our integrated model basically accommodates agricultural model and industrial model. Here I present very briefly the agricultural model comprises different farms. Each farm is a decision-making unit, and it is more or less independent from the other farms. Sometimes there are some common resource constraints, and then we have policy constraints that affect the behavior of farms. There is a lot of literature here, and because those models are standalone, we can take into account modeling advances like considering risk analysis or different modeling methodologies. Here is just an algebraic, very short view of the relationships that are in the model, the objective function, which is the welfare of the farmers. We have physical constraints, technical constraints, policy constraints. The decision variables include basically land, crop areas that are selected from the model to be cultivated in the region. So the variables come in terms of hectares for different crops that are cultivated in the region, including energy crops and residues from different crops currently or cultivated in the future. The second component is the industrial model. The industrial model runs on the basis of an objective function that is the return on investment. So we modelize the industry, so different units. I will talk a little bit in more detail later. And the support, the modeling support, is the general algebraic modeling system, which is GAMS. GAMS is a quite powerful modeling system, including code, solvers, and interface. It is a pretty straightforward algebraic language, so it's not very strange for engineers to model. They don't need a special training. And using this language, we integrate all the components into an integrated system. This is the basic information that is included in the industrial model. So you see, we have different types of technology and size of plants. This is the first column. In the second column, we have the power that can be generated by each one, the installed power. So we have, as you see, we have from very small to quite big plants. Here we consider two technologies. We introduce parameters such as the investment cost, the um, different prices that um, are prevailing in the market, operational costs, and based on that, we have profit and calculate the return on investment. So each technology can be um, be fed by mix of feedstock. So in this case, we have biomass from plant and livestock. We have considered sorghum and manure. So for each size and technology, we know based on the installed power to produce a unit of energy, how much of the feedstock we need. So we can calculate the volumes and then of course we can calculate the output, which is energy and digestate. So based on the price here, for illustration purposes, we calculated the return on investment. You see that the return on investment is not necessarily increasing by size. The optimal can be something in between, because in reality, prices that are and support that is given by the legislation is depends on the size. So there is different combinations of prices, and in this case, this is just to show the calculations. When the model operates, the the price is an input to the model, and based on the other parameters, technology, operating costs, and so on, we derive the profit, let's say the return on investment. So when we run the model, each unit, each theoretical unit of biogas is entered in the system. The model selects the most efficient unit. The most efficient unit is able to pay better price to the farmers and requires a certain quantity of biomass. So this biomass is demanded by the agricultural model that supplies the biomass. So and once the most efficient unit is satisfied and covers the capacity, then the model goes to the next most efficient unit that enters the system, buys the biomass because it's the most competitive, it's most efficient, so it is able to offer a competitive price to the farmers, gets the biomass from the agricultural model, and so on. So this is an iterative use of the model, and the iterative use generates what you see here, which is the demand curve. So this is a demand curve that comes after a certain number of iterations, because I don't have a dynamic presentation here, but it's the final demand curve that is generated from the industrial model. In the case study, now I have the real numbers here for the region. Um, we can allocate spatially. We know where the biomass is cultivated, so we can using the transport cost figures. The most efficient industrial unit is also spatially located, so we can determine the model can determine where is the siting of this unit. So it comes together with the technology. The location is a parameter in the model. We can visualize this in the map. Here is the flow chart, so is the state-of-the-art technology that we use. We have the coefficients and so on. This is everything is in the model. Um, we can use different parameters for policy depending on the feed-in price, and we also performed a kind of sensitivity analysis. So the return on investment is sensitive to the feedstock price, the feed-in tariff, and in a lesser extent, investment cost and the interest rate. So to show the results, here is a graph that combines the demand and the supply. So the orange curve is the demand, and the blue ones represent the supply. You can see that they intersect somehow, and this is the market clearing equilibrium. We have two curves for the supply because we simulate different agricultural policy frameworks. As you probably know, the common agricultural policy is the main factor that determines agricultural supply in the countries and is the same for Poland. So there are every now and then reforms in agricultural policy, so the model can accommodate different parameters regarding agricultural policy. So we have the market clearing, and we can project on the map the supply and demand, so we know which regions supply biomass, and this is, I think it's allocated based on municipalities. We can also represent the results in lower scale, so in smaller areas. So here, for instance, we divided the problem in two sub-regions, let's say in the northern part of Lubelski and the southern part. So as you can see, the supply and demand, the blue line and the orange line, I think belong to the south region, and then the others. So we have two equilibria, and this is the result of the model. So as a conclusion, we can have at the optimal solution the number of biogas plants that are efficiently operating according to the model in the region. So here we have indicative number of 93 biogas plants. Imagine that at the time, it's a couple of years or maybe 3 years ago, that we ran the model in the entire country of Poland. The number of biomass plants was around 130 or something like this. And in Lubelski, we had, I think, two or three. So the economic potential for biogas production is many, many times higher than the current situation. Simulated plants, so the optimal solution show us that we should go at 2 megawatt of installed power. So This is another finding of the model. High demand of biomass for energy. So both residues and sorghum are demanded by the model. And sorghum is quite efficient bioenergy crop, and the model results in considerable amount of area that could be dedicated to the sorghum cultivation for bioenergy purposes. And mainly this, I can tell you that mainly this area would be in let's say, in mostly abandoned land, because sorghum is quite productive even in low fertility soils. So another finding is that there is lack of regulations for raw materials market necessary to generate biogas. And there is necessity to prompt residues utilization in order to avoid competition between biogas and food crops. There is a considerable amount of feedstock from residues that is selected by the model at the optimal solution. So that means that residues render more efficient the biogas industry. Um, in the next steps, we aimed at investigating different scenarios, take into account technology progress. For instance, now we have good data for state-of-the-art biogas plants that they are demand-driven, so they are flexible because they are able to stock the biogas and then use it during peak demand. The advantage of the model is that because the let's say the components are distinct, then we can take into account different parameters for the industry to add, for instance, another technology in the candidate technologies, and then see what happens, the optimal solution. And because also that agricultural component is separate, then we can simulate different regulations, so agricultural policies, for instance, or policies that support bioeconomy development. Because of the detail of the model, we are able to generate at the optimal solution not only the economic outcome, so that relates to income or profit for industry and so on, but we can also derive figures that relate to environmental impacts, for instance, the use of fertilizers or greenhouse gas emissions from industry or from the agricultural sector. So we can use the model in, say, multi-objective manner, or to control different impacts that are of interest for policy making. So this is more or less very schematic presentation of the model and the capacity of the model to derive results that are related to the bioenergy industry. That was the example of biogas. In technical terms, I can say that this is a model that runs for the region. It takes a few minutes, maybe 10 to 15 minutes. So it's not a model that it's quite heavy. It's not a model that can be used for interactive decision making, but it can give valuable results at the regional, and also this is part of another project at national level. Thank you very much for your attention.
We thank you, Professor Rozakis. Since I have you at hand, um, there's a question for you from Francisco Patrocinio.
Mhm.
Um, he asks if you can shed the light on which model type are you using? Is it MILP or MINLP? The model size, the number of variables, or the number of questions. Uh, in terms of the number of variables, he asks if it's like a continuous or a binary. And if it's MINLP, where did you implement the non-linearities?
Well, this is, we have different versions of the model. Well, to give you an idea on the size of the model, we have about, let's say, for the agricultural model, about 10,000 variables and 5,000 constraints. So the industrial model is much less large. We use integer optimization because of the technologies. And if you want to know which solver, we use different solvers that are in the GAMS frame, either Minos or Conopt. Uh, the model is not necessarily non-linear. I mean, the basic version of the model is just integer linear programming. There is a non-linear version when we introduce the risk in the agricultural model. So in this case, we have in the objective function non-linearity because we take into account variance of the income and not the income itself. So in this case, it becomes non-linear. But because the two models, agricultural model and industrial model, run sequentially, so they are not in the same, let's say, in the same model. They don't optimize, let's say, they don't optimize together. They optimize sequentially. So first we run the industrial model, we select the most efficient unit, then we inject the parameters, the results of the industrial model that are input for the agricultural model. Then we run the agricultural model, we get the biomass quantity and price and so on. So because they run separately, then the non-linearity is not a big problem for the integrated model. So of course it takes more time, but it's I think it's an advantage of this modeling framework because um, the modeling team can depending on the available data, on the capacity of modelers to represent the agricultural sector. They can use more complicated or more advanced models. For instance, some people apply positive mathematical programming, which is also a non-linear algorithm. It can be accommodated in this modeling framework.
Um, Thank you for the answer. And last, we have a few questions for Mrs. Brasio. Um, if you can hear us, Anna? Perfect. Um, Joao Pinho asks whether you could disclose whether you're using a recombinant yeast or co-fermentation to consume both C5 and C6 sugars to produce bioethanol.
Yes, I can answer these two questions. One is regarding the reaction or the process, and the other regarding the feedstocks and the usage of acacia. So, regarding feedstocks, I would like to start by the beginning. Feedstocks for us, in first place, tell that this cooperation between PRIO and the other entities, and here with the companies and the institutes that promote biomass, like Floresha and CBE, is very important for us companies because they have all the knowledge that we need to develop this type of projects out of the box. So, out of the box, and I can say additionally that, of course, we have a lot of knowledge in the literature, but there is a challenge, and still there is a gap between in research and in industry. And because of that, it's important to shorten this gap, bring together the companies or the institutes that can provide the knowledge developed by them or by the past by others. Here, CB and Floresha are very important because they know the market regarding this type of feedstocks. We chose specifically these 5 types of feedstocks because there are at the moment available to processing, to develop valorization. Here I'm talking concretely about the phase of collection of this type of biomass and availability to several applications. Floresha have this knowledge that this type of agriculture residues are at the moment available to deliver to industry or potential clients. And regarding the forest residues, they are already used in these biomass centrals to produce energy, thermal and electric energy. So we need to look to this type of feedstocks in order to avoid the limitations of collection and the availability to the applications. Of course, we could thinking on about acacia, but today acacia is not available in so much quantities. And I don't know about the prices, but in quantities enough to use them without additional investment in this pre-phase. Regarding the technology, LENEG is an important partner in this project because LENEG has a lot of knowledge about the technology. They developed a unique technology that promotes more better yields, that promote better investments, lower investments, and because of that experience in lab and in pilot scale, they study a lot of optimizations regarding the process, and specifically regarding this conversion of sugars into bioethanol, not looking only for one type of sugars, but all the types available, C5 and C6. We also studied simultaneous saccharification and fermentation, and this question of in situ enzymes production is also very important in order to reduce the OPEX, the operational costs on enzymes. Producing these enzymes in situ, it's an important thing to have. Of course, this we evaluated also the additional capex that we need to put on this production. And for the project we are developing, it's important to have this in our facilities and not to buy to external providers.
Thank you. You answered actually both of the questions, which is perfect because we're past our allotted time. I'm not going to ask any additional questions. I want to thank all of the panelists for participating. I want to thank all of the attendees. I want to thank the University of Coimbra for organizing this event. And also to remind you that you can find the recordings on the Bioreal Toolkit. It will, of course, there will be some time until they are uploaded, but soon enough they will be there. And yes, I think that's it for us.